Hey y'all, and welcome back to Coding with Minh. On today's agenda, we're going to tackle a classic LeetCode problem, 146, LRU Cache. After that, we'll go over an actual variant of the original question that Meta asks. It's fair game whether you get one or the other, so please know both. Let's start. We need to design a data structure that follows the constraints of a least recently used cache, or in other words, LRU. We'll implement an LRU Cache class with the following functions. LRU Cache, a constructor, initializes the LRU cache with positive size capacity. A get function that returns the value of the key if the key exists, otherwise return -1. Put updates the value of the key if the key exists, otherwise add the key value pair to the cache. If the number of keys exceed the capacity from this operation, evict the least recently used key. These functions get and put must run in big O1 average time complexity. Okay, wow, I'm tired from reading. What did this all mean? No clue. Let's just go through a few example function calls and visually observe what unfolds. Let's see what happens if we call the put function with a key of 1 and a value of 1. Oh, cool. What if we call it again with a key of 2 and a value of 2 this time? Very adorable. Third time's the charm. What about a key of 3 and a value of 3? Nice. All right, let's switch gears. What about a get function call? Let's invoke it with a key of 3. Thank you. This returned to us a corresponding value of 3. Great. What about a get call with a key of 4? That's expected. -1 means there was no key of 4, and clearly there isn't. Our task is to implement an LRU cache that implements everything we just saw in the demo. Also in such a way where each call can be executed in a generalized big O1 time complexity. The big question is, how do we implement this programmatically? Or more specifically, what types of data structures should we use to implement this LRU cache? Let's reinspect our cute little demo just now and look at it through the perspective of a casual LeetCoder. Okay, much better. It's all techie and stuff. All right, so we had two functions we must implement. It was the getter and essentially a setter. If we call the put function to insert a key of 4 and an associated value of 4, in big O1 time complexity by the way, then shouldn't a hash map be the data structure of choice? Indeed, yes. That function call felt weirdly empowering. Let's do it again, inserting a key of 5 and a value of 5. Now, what happens if we call our put with an existing key of, say, 3 and a new value of 30? It does what you think it does, or not. The LeetCode description didn't spell this part out for us, but anytime we call the put function, or the get function for that matter, that entry becomes the most recently used element, opposite of our least recently used, and thus must appear at the tail of our map. I'll tell you right now, this desired behavior introduces an issue for us. When we call any method on an entry, we like to push it back at the end of our map, and essentially act as the new tail. At its core, a hash map is an associative container, meaning it's not sequential. You can't easily append the most recently used entries at the end. If we were to insert into our map a key of 6 and a value of 6, it may appear here, here, or here, all three of which are not correct. What do we do? Well, one thing's for certain, we must enlist the help of another data structure. The natural follow-up question is, where does a new data structure fit into the picture? Is it meant for the keys? Is it for the values? Is it for the key and value? Here's the overall thought process. We already have a fast mapping from key to value, so we don't need to mess with the key at all. This leaves the remaining values of our hash map. So allow me to rephrase my question. What non-associative data structure do we need for our values? I'm not sure, I'm not smart like that. Instead, let's just YOLO and try some data structures. I kinda implied it earlier, but we need a sequential data structure, one that easily allows us to append values at the end. Obviously, as options, we have a list, a singly linked list, and a doubly linked list. There are others, but these are the main ones. A list is the most basic one. Let's try it out. If we call, say, get with a key of 2, then it's pretty inconsequential to move a value of 2 at the end, as well as recreate the mapping, right? Sure, but this comes with a huge cost. Removing a value in the list is an n-squared time complexity operation. It's too expensive for our liking. We're trying to get a job here. Let's try for a singly linked list. Once again, let's say we call get with a key of 2. Like our list before, being a sequential container, we can easily move the value of 2 at the end of our map. It's as simple as setting the right pointer. But there's this one issue. How do we rewire pointers and untangle these pointers of where node 2 was? To answer this, we look up a key of 2 in big O1 thanks to our map and access the corresponding node value. With a reference to this, we'd ideally like to set the right pointer of the node before, the 1, to the node after, the 4. Clearly, we can't do that. We're lacking a critical node reference specifically to the 1 before. Alright, don't lose hope. We have one more sequential data structure to try. It's a doubly linked list. All it means is that every node has a reference to the node to its right, but also to its left. Wait, this is exactly what we needed, a reference to the node before. This makes it possible for us to rewire the pointers as such. Our node 2 is now untangled and removed from this web of pointers and now can be moved to the end. It's the new tail of our data structure, you could say. And just so you know, nodes are objects that live at memory addresses. We're not actually removing it, we're just moving it. All this to say, our map's key still points to the same memory address of node 2. But with that said, that is the intuition to arrive at implementing a least recently used cache. There are more fine details, so why not explore them? Okay, let's start from scratch and call a chain of function calls and see what happens at even lower level implementation details. We'll initialize an object of our LRU cache with a capacity of 1. Recall this requirement. If we ever have more than one node, we'll have to remove the least recently used one, so the head node if it exists. First up, let's call the get function with a key of 9000. Wait, I'm drunk, the node doesn't exist. It's nothing we can't easily check with our map though. If this is ever the case, we'll return -1 as instructed by the problem description. However, more sanely, let's call put with a key of 1 and a value of 1. Great, this is technically both the head and tail nodes, right? If it wasn't immediately clear from before, the head node should point to the least recently used node and the tail should point to the most recently used node. And while we're on this note, keeping track of the tail node is critical. That's how we'll easily move a node to the very end, rewiring the pointers as appropriate. I'm yapping at this point, let's see it in action. We'll call put with a key of 20 and a value of 2, inserting that into our map like so, and pointing the pointers. Just like that, we're done with the function invocation. Or are we? Recall our capacity was 1 node. We have 2. In the cases we insert one too many nodes into our LRU cache, we're instructed to delete the least recently used, or in this example, node 1. I'll tell you right now, we can make it work, but doing so is a pain in the butt. We'd have to reassign both the head and tail pointers to node 2. And if we put another node, we'd have to annoyingly take care of the same problem. Reassigning the head and tail pointers, we can do better. Allow me to introduce to you a common technique when working with linked lists, dummy nodes. They're dumb because they don't do anything other than exist. Their main purpose in life is to upgrade our head and tail nodes to be first-class citizens. Let's debut our 2 new nodes, rewind the deletion of node 1, and see how much of a headache this saves us. Remember, we reached capacity after inserting a key of 20 and a value of 2. As to how we delete node 1, we can grab 2 useful references, specifically to the node before and the node after. I hope this is familiar. This is all we need to set the pointers, setting the right pointer of before to after, and the left pointer of after to before. If you're one of those people who likes to see the code behind it, here it is. The last thing we need to do is erase the mapping in our map, and voila, we are done. Okay, let's go through a few more calls of get and put and consolidate the functionality. Let's actually increase our capacity here to perhaps 3. Sure, why not? Let's call the put function with a key of 3 and a value of 3. We'll create a new node with a value of integer 3, insert it into our hash map. Right. Recall, maps aren't sequential. If you insert an entry, it's fair game, it appears anywhere. So we'll do one last thing and move node 3 to the end. As to how exactly, we'll need the node before our tail to set the pointers and then assign before right to the current node, left pointer of current node to before, and then similarly, current right to the tail and tail left to current. That was not coherent. To see it better, we can formalize it in a helper function. Amazing. That was so fun. Let's do it again. This time with a key of 4 and a value of 4. Like before, we'll spin up a new node, insert it into our map, and then call our move to end helper to move the node to the end. Remember, this is the most recently used node and thus should appear last. And you know what? I'm having the time of my life. Let's do it one more time with a key of 5 and a value of 5. Everything happens as you'd expect. Great. But hold on, we exceeded our capacity. We can only have 3 nodes, but we have 4. We did it once before, and we'll do it again. In the situations we overflow the number of nodes we can have, we're instructed to delete the least recently used one. Or in other words, the node to the very right of our head pointer here. We can rewire our pointers, which we call with something along the lines of this formula. Something something before, something something after, and done. Deleted from existence. The last thing we must do is remove it from our mapping by a key of 20. But wait 1 second, we don't have a reference to a key of 20. This is problematic because we'd have legacy keys in our map, leading to memory leaks, among other issues. Let's not panic, think calmly and ask, what do we have references to? In retrospect, before we deleted it, we had access to node 2, right? Why not stuff the key in that node as well? Nothing stopping us from stuffing as much state as we want in our class design. Let's do it. Amazingly, with this, we have a reference to the key and thus be able to erase the mapping. Moving on, let's do one final put function, last one I swear, but this time we'll invoke it with an existing key of 3 and an updated value of 30. We know it's an existing key in big O1 because of our map, so we can access node 3 with ease. After that, we'll do a laundry list of things. 1, since we technically used this node, it has to be deleted via our ever so reusable rewire pointers function. And 2, move to the end of our LRU cache, also using our move to end helper function. Awesome. As the final function call in our chain of calls, we'll call get with a key of 4. Like we observed before, get a reference to the node by the key, save to a variable the value of 4 so we can eventually return it. And then as always, we'll rewire pointers since we technically use this node. Since this usage makes it the most recently used, let's call our move to end helper function to move it to the end. And that sums up the logic. You may have guessed it, but there's a hefty wall of code we have to write. Let's get started. Alright, before anything, let's define our node schema. It'll have pointers to the node to its left and the node to its right. This will make up the building blocks of our doubly linked list. Of course, it'll have an integer value, but less intuitively, the key. Recall, we'll need this to be able to know which mapping to remove in the case we have too many nodes. Let's initialize a constructor to initialize both the key and the value. Great. We'll utilize these nodes in our LRU cache, first and foremost as head and tail nodes, as well as a map from the key, which is an int remember, to said nodes. We'll call it something like key2node. Makes sense to me. Of course, we also have the capacity, and that wraps up all the class fields for our implementation. In the constructor, let's initialize all of the aforementioned state. It doesn't matter what key and value our dummy nodes have, so we'll randomly pick -1, -1. Same with the tail. What we'll do is set their pointers to one another upon initialization. This is logical since there exists no nodes yet. I know I'm eager to get to coding the functions, but let's make sure we're fully prepped. Let's write up our helper functions. First, we have the move to end method that takes in a node. This will literally move the node to the end of our doubly linked list. Let's get a reference to the node left of our tail and call it before. And with this, we can modify the pointers as such. Before right to current, current left to before, current right to tail, and tail left to current. After this, we have one more. We have a rewire pointers function that will essentially remove a reference to a given node. Let's make sure we have access to the node before, as well as the node after. Then, to exclude the current node, we'll set before right to after and after left to before. Okay, let's implement our much anticipated get function. First up, what if our key doesn't exist? Easy, we'll return -1. Otherwise, we'll get a reference to the current node via our map, and from that, the current node's value. Let's return it before I forget. Last two things we'll do is, since we use this node, we'll rewire its pointers and move it to the end. You see how easy that was? At last, we have our put function. What if the key doesn't exist in our map? Well, we'll create a new node with the key and value parameters. We'll insert it into our map, like so, and move it to the end. since it was technically used. After, if inserting this node surpassed the number of allowed nodes, the capacity variable, then we need to evict the least recently used node, which, for reference, will always be to the right of our head pointer. We'll rewire its pointers to lose a reference to it, and then erase it from our map. Now, what if we call the put function on a key that does exist in our map? Before anything, we'll get a reference to that current node that we're updating, and we'll actually remove it entirely from our map. But then after that, go through the same exact logic to recreate the node with the updated value and insert it into our LRU cache. It'll fall into the same logic, including the capacity check. How convenient. And that's the implementation. If I made a typo, don't at me, but if I didn't, I'm just that good. The variant is tricky. Let's get into it. Welcome to the variant, where most of the requirements remain the same except for two additional functions, namely the delete function and the last function. The former deletes the key value pair if the key exists and returns true, otherwise return false. And the latter returns the value if at least one entry exists, otherwise return -1. Furthermore, the get, put, and delete functions must each run in a big O1 average time complexity, with the exception of the last function, which should run in a generalized big O1 time complexity. If you're a clever human, you'll observe that there was no mention of a capacity variable. You'd totally be right. There is no ceiling to how many nodes our LRU cache can contain. And that summarizes all of the requirement changes. What's our plan of attack, you ask? We'll continue from where we left off from the original LeetCode problem and simply extend its functionality. As a disclaimer, I won't be re-explaining things since that'll just put you to sleep. And surely, it's not like everyone skips straight to the variants, right? Like I said, there is no longer a concept of capacity. We can call the put function as many times as our heart desires, or at least until we get an out-of-memory error. Point is, we won't be needing the capacity class variable anymore. Let's vanquish it to oblivion. Thankfully, our two functions, get and put, both remain unchanged. But we have some new functions to implement, one of which is the last function. Remember, all it'll do is return the most recently used node. We're very happy we spun up a dummy tail node. This is literally the only reference we need to return the most recently used node, the 4 in this case. Please note, if we have 0 nodes in our LRU cache, then if the left of our tail is our head dummy node, then we know there aren't any nodes yet. We return -1 as instructed. Easy peasy. But let's wait, pause, and reflect because critical thinking is fundamental. Why can't we only use a map data structure and exclude a doubly linked list? Meaning, whenever we call the put or get function, can't we assign the tail pointer to it? If every time we use a node, it becomes the most recently used one, then we can simply keep a reference to it. So, if we hypothetically called put with a key of 9000 and a value of 9000, this becomes the new tail, and thus makes our last function operate as expected. 9000 is indeed the most recently used node. Similarly, if we call get on node 4, then that becomes the new tail, the most recently used entry. There's just one problem. We still have to code the delete function. Let me ask you this. If we deleted node 4, then how do we know what the second most recently used node was? Remember, we only have an associative data structure, the map. Therefore, we have no idea and our code doesn't work. This is all to say, we still need the doubly linked list. You can think of it as the combined magic of a sequential and associative data structure. Quite a tangent, I know, but let's now implement the infamous delete function. It does what we think it does and removes a node by a specified key. Let me demonstrate. If we call it with a key of 9000, then that means I'm a dummy, not any better than our dummy nodes here. A key of 9000 is nowhere to be found. But hold on, there's something to be learned here. If we invoke the delete function with a key that doesn't yet exist, we'll return false. Edge case covered. Otherwise, if we invoke delete with a key of, say, 5, then all we'd have to do is rewire pointers, reusing a function from the OG LeetCode problem, and then erasing the mapping from our map. Unlike before, this was a successful removal. so we'll tell the client by returning a boolean of true. Anyway, we're a madman on a destruction spree. Let's demolish node 4. With the help of rewire pointers, this removes all pointers in node 4, thus deleting it. Not technically, but you get the idea. As always, we'll erase this mapping and return true. The taste of chaos is quite addicting. Let's continue our rage of fury where we'll delete node 30. 1. Rewire pointers. 2. Remove the mapping. And 3. Return true. We have nothing left. We can finally rest in solitude. Hi, how are you? Alright, let's get to coding. Recall that the capacity is no longer a concept in our LRU cache. Let's remove all references to it. This includes our constructor, but also in our put function here. There's no such thing as one too many nodes anymore. Other than that, the get and put functions remain unchanged. Good for us. After that, however, we have the delete function. It'll take in the key of the node to obliterate. Remember our edge case. If our map doesn't have this key, we'll just return false. And before we continue, let's collapse some of these private functions. We already know what they do, so why not abstract them from our minds? Anyway, if the key does exist, we'll get a reference to the node that we do want to delete by the key, rewire its pointers, erase it from our mapping, and lastly, return true. Lastly, no pun intended, we have the last function. To get the most recently used node, it's literally one node to the left of our tail. Let's access it and return the value. However, if there aren't any nodes in our LRU cache to begin with, and we know that because the tail's left node is our dummy head node, we'll return -1. Amazing, that's our implementation. It's a lot of code, so make sure you practice some typing tests before you apply it to big tech. And with that, I wish you luck on your interviews. Hey y'all, editing Minh here. I realized in post that I didn't have any room for pop-ups of tips and tricks. It just so happens that with this LeetCode problem, there are upwards 7 of them. As a remedy, I thought I'd just rapid fire talk about them all at the end. Let's do it. 1. As an FYI, this LeetCode problem serves as a thin base for one of Meta's most difficult system designs, Design Memcache. 2. There is obviously a lot of code to write in this problem, so it's best to write helper functions as early as possible. It'll not only save time, but also error-prone typos and mistakes. Another tip, Meta will most likely, but not always, paste the APIs in your CoderPad IO, and it'll be up to you to implement them, so no need to write the function signatures themselves. Also, especially with this kind of problem where it's extremely visual, don't keep it all in your head. Try to draw using CoderPad's inbuilt drawing mode. It's faster and super efficient to guide your verbal explanation. You can type ASCII, but that's very time-consuming. This one's a bit more of an FYI, but when we rewired pointers, I said it essentially removes the node. In reality, for languages like C or C++, it's not actually deleted. It's known as a dangling reference and will contribute to a memory leak. If you're using C or C++, first off, why? But secondly, make sure you point this out. It's always best to delete it, using smart pointers ideally, and setting it to null pointer so no one else messes with it. Here's another tip. Meta may give you a variant where the node values are templated, meaning your whole LRU cache may be generic and could contain any user-specified data type. Make sure you're ready. And at last, the delete function in the variant may very well have a void return type. You'll immediately know what the method contract is the moment your interviewer pastes it. But in the case they don't, make sure you ask and clarify. Thanks for sticking it through. And if you learned something today, please make sure you like, comment, and subscribe. Thanks.